with another part of the heap. Then we need to get the first chunk allocated back right to it, then allocate a chunk of memory larger than 512 bytes to cause consolidation. The malloc consolidate code, it first goes through and it finds the next chunk. However, because we control the pointer, the next chunk is actually, what we can do is point it to ourselves. When it goes through and does a loop, and it says pointer to next, basically. And so we can basically fake a chunk in there and cause it to process our chunk, and kind of shift it down into ours. So we don't get it on the first time through the loop, but we'll get it through the second time. In order to bypass the coalescing of previous and next chunks, then we have to have bit 0 or the low order bit turned on, mark that the previous is in use. Otherwise, we hit the unlink macro, and depending on the specific state, we potentially won't survive that. We may cause the same thing as what you get if you try to write a buffer overflow using the unlink techniques. And additionally, the next chunk also has to have its previous in use bit set on. Not really a problem, actually. You'd think it'd be a little bit more difficult than it is in that, at least in that initial transition. What we actually do, though, is we abuse the clear and use bit at offset, which takes two arguments, the pointer and then an offset, and it actually turns off the least significant bit. So what we can accomplish there is turning off a bit at any particular address that we'd like. So yeah, you get off by ones, and now we're talking about flipping individual bits. In that, it's useful, but it's hard to hit in any place because of the fact that you have to have those two low order bits to avoid consolidation. So you either have to go through and find a place where that instance is true in both instances, or that those conditions are true in both instances, and what you want to write is actually useful, or you have to have some limited control over what data is before and after. The stack being the most obvious place where you can potentially do that. The next technique is similar, but instead of using the clear bit and the clear and use bit at offset, we're using the set head macro, which it essentially just takes the size, takes a pointer and the size, and then ORs it with the previous in use, which in turn means that we can take a pointer plus 4 bytes if you're assuming a 32-bit integer, and turn on the least significant bit there. And you can do that with any particular byte. If you can actually get enough control in the stack to fake chunks in there, you can cause multiple writes to occur. However, again, you have to have those two conditions where you have to have the low order bits turned on both prior and after. This was actually, again, like I said, if we like off by ones, then you can actually do a lot with flipping on one bit. It was an interesting one to play with. I think I duplicated this slide. I apologize. The next instance is that we can actually, if there's a check in the consolidation code that checks to see if the next chunk is equal to the top chunk, and if it is, then it folds it in and assigns the top pointer to the pointer of your what you control, or your pointer. If we can control an integer on the stack, or even have limited control over it, then what's actually possible is that we can take, regardless of where our pointer is, we can actually make it add up to what you do is you do 0xFFFFF minus address that you're wanting to write to, or you're wanting to set the top chunk to, plus address of the top chunk. And that yields, and so that when it actually calculates the address of the next chunk, it looks like you're right next to it. Which in turn, what happens when the top chunk ends up being pointed to wherever you'd like it to be, Then whenever allocations occur that aren't filled out of the free list, it occurs, you get pointers back to wherever you just pointed, or wherever you set the top chunk to. So if you were to point it to the stack, for instance, instead of having a chunk of memory that gets returned by malloc or realloc that points to the heap, you get it pointing to the stack, which in turn is going to cause any number of problems depending on where you point it at. The biggest issue there is that you have to have that integer, and you have to know what the address of the top chunk is. Getting back to the multi-threaded stuff, what we have is actually the section of the code at point 0 there. You see that the chunk gets allocated, and in the ... there, it actually processes and performs the writes, and if it increments the pointer as it goes through. And if the last element is over 128, then it calls free OID, which in turn causes which calls free itself, and then free mech type calls free OID, which in turn calls free. So what we're attempting to accomplish here is to get one thread in between point 1 and point 2 prior to the allocation actually occurring at point 0. And the slide basically just says what I did. But if we accomplish this, then basically what happens is that the first thread frees the chunk, then the second thread allocates that chunk back to itself, and then the first thread causes the double free. This allows us to bypass the normal bin double free checks. Now, the biggest problem that occurs here is if both threads start at exactly the same time, then how are we going to get them at different places at the same time? And that's not really even dealing with any real-world issues such as network latency or delays or other clients that are connected to the server. So for the sake of purposes here, we're just going to consider a lab to kind of give you an idea of how to accomplish this. The first idea I had when I looked at this was try to use the mutexes against each other to allow them to sync themselves up, basically. The biggest problem that we have there is that malloc doesn't actually call pthread lock, it calls pthread try-lock, or pthread mutex try-lock. And if that fails enough times, then it's actually possible for a new heap to be created, which is absolutely the last thing we want. Second idea that I had was inside of malloc, when it fails to acquire the lock, that is actually it calls pthread mutex lock on the list lock. And so the idea was to get 3 threads in there, 2 of which racing for that lock, and 1 blocking the other one, while I get the first free to occur. That wasn't really considered, basically because, as I said earlier, we're trying to reduce the complexity, and the more threads that we stick in there, the bigger the race that we're trying to win is, and we're already talking about a very small slice of time. The first thing I looked at is, is this a valid concern that I have? Do I really need to worry about this? And indeed, I did. So I tried to find a shorter path through the code, and this isn't. I took took timestamps from the processor to get an idea of just how long single iterations through loops and how long it was between point A and point B. It's definitely not something that. It's definitely not the most accurate and not the most consistent. As you see when I start talking about the different amount of ticks that it takes an operation to occur, it varies wildly. But it did give me a general idea of how long a particular operation took place on average. So when I looked at it, and I wanted to see how long it took to get from point 1 or point 0 to point 1, I ran using minimal data so that I minimized the amount of times through the loop. I think I used 1 byte. Ran the test 10,001 times. The highest amount of clock ticks that it took was 379,000, whereas the lowest was around 5,600. Which gives you an idea of just how long and how much variance there actually is in the amount of time that it takes for any particular set of operations to occur. However, the average was about 13,000. Went ahead and rounded it to 13,200. So the goal here is to try to save somewhere around 13,200 ticks in hopes of shortening the execution path for one of the threads. When I went through, there was multiple places that there were loops. Unfortunately, there weren't as many as I had hoped. The code was by and large, or in many places, was done in constant time. The big ones being the base 64 decode length and the actual decode of the data, and then the function dir get OID. By looking at those functions, I was able to find a shorter code path that actually resulted in the same size chunk being allocated. An APR base 64 decode length. It's a simple while loop that iterates through a pointer to user data that looks it up in a character array of 256 cards to verify that it's actually valid base 64, and it keeps walking through until it hits the end of the string or the data is no longer valid base 64. Again, when counting the ticks for just a single byte, trying to determine how long it took between 260 and 305 ticks depending on the characters used, and that's because of the actual placement in the array. The high was around 688,000 to 245,000 depending on which character was used, with the average being between 602 and 573. After I ran all of the tests, the average was about 600 ticks per byte saved. So if we can cut up to 8 characters, this is approximately 4,800 ticks saved. And if we cut that out, we also have to consider the base 64 decode function, which is also going to get a shorter execution path due to having less data. Ran again 10,001 tests. High tick count of 4,000 with a low of about 1,000, average being about 1,100. Went ahead and rounded it up to 1,150 and multiplied by 8 for each of the 8 bytes that we can emit before we actually get a different size chunk. Multiplied that by the 4,800 ticks that the decode length function saved us, and it actually yielded 14,000 ticks, which is higher than what we were trying to save. In addition to that, we actually needed to consider dir get OID, unless we cause an error earlier on. However, that's not going to suit our purposes because we actually need to hit that free to cause the chain of events to occur. There's 2 different code paths in the loop depending on if the byte being processed is greater than 128 or 80 hex. If it is, then it actually enters a do while loop inside of the other loop. So I had to test both. If an individual byte was less than hex 80, then the high was of 4,000 ticks with a low of 5 ticks.